Okay. Welcome, Nicholas and Shania, and wow, and Max. I don't know if I'm saying your name correctly. Shania, it's two ways. Okay. Polarity. Remember last time we said if there's an uneven distribution of electrons around the central atom, then, so it's slightly negative on one side and slightly positive on the other, we say that there's a separation of charge. So we have a more negative end and a more positive end. And that separation of charge we call a dipole. Now there's two different types of dipoles. There's a dipole in a bond caused by an uneven sharing of those bonding electrons. And then there's that overall separation of charge for the molecule. So bond dipole is the separation of charge in a bond. And so would you get bond dipoles in a polar bond? So yes or no, who would like to answer? So I'll just repeat the question. Would we get bond dipoles in a polar bond? Yes, correct. Would we get bond dipoles in a non-polar bond? No, correct. You will find at level 3 there's sort of those sort of exceptions because of the way the molecule is, but pretty much at level 2 you can state that. If you've got the same atom bonding to each other, like oxygen with oxygen, you've got no bond dipole because those electrons are equally shared and the bond is non-polar. But if you have something like hydrogen and fluorine, they have got different electronegativities, so they share unequally. Fluorine attracts those bonding electrons a lot more strongly, and so you're going to have a polar bond and therefore a bond dipole. Now, the shape of the molecule will say whether you're going to have a molecular dipole. In other words, this is a simple one because I've only got one bond. So the molecular dipole will be the same as the bond dipole. But it doesn't have to be the case. And I think the best way is to do through example. So this is just a revision of what we did last time. Remember, to work out whether a molecule is polar, you need to know the shape. And how do you know the shape? What do you use to work out the shape of a molecule? It is pretty much written up there. Emma is typing. Okay, the Lewis structure. Yeah, so you look at the Lewis structure, and the important thing about the Lewis structure is you have to then count the number of electrons, or not so much electrons, count the number of regions of negative charge or regions of electron density around the central atom, not just any atom, it must be the central one. And then that will tell you the electron geometry, and then you look at the bonding and the non-bonding, and all this comes from the Lewis structure. You can see it all from the Lewis structure, and then you can work out the Lewis shape. The molecular shape. Okay, and then you look to see if the bonds are polar, and by looking at the electronegativity, and then you check if those bond dipoles are going to cancel each other out. And let's look at it now. So first of all, what do we mean by electronegativity? There are the three types of bonding you have to learn this year: the ionic bonding, the covalent bonding, and the metallic bonding. Now it's never that, all these are covalent and all these are ionic and all those are metallic. There's actually really a continuum along it. So you have electrons being equally shared in a pure covalent bond, so fluorine, oxygen, chlorine, Cl2, O2, F2 would be down here. But as they bond to other atoms, so here I've got F2 being bonded, but now it's bonded to O, which is a little bit less electronegative, there's an unequal sharing. If the F bonds with nitrogen, there's even a more uneven sharing of those bonding electrons. So we get what we call a difference in electronegativity getting bigger and bigger until we've got a very ionic bond. The cross-off point, depending on what literature you read and so on, is anything from about 1.7 upwards. BF3 is considered non-polar, and that has got a difference of 2, but so anything from 1.7 upwards is starting to be considered a polar, an ionic bond, where the sharing is so unequal that it's considered that the one has all the electrons and so an anion, and the other one has lost an electron and so is a cation. So do you get this idea of sort of the sharing becoming more and more uneven until you get to the ionic? Does that make sense? Yep. And you can have the same continuum along the metallic bond, ionic bond system, and the same thing along the covalent to the metallic bond. And we'll look at the metallic bond in more detail later, so I'm not going to deal with that now. What I really want to focus on is electronegativity, because we need that for polarity. And remember, electronegativity is a property of an atom, not of a molecule. You can't say the electronegativity of water. That's wrong, because water is a molecule. You can say the electronegativity of oxygen or the electronegativity of hydrogen, but not of a molecule. Okay, because you're looking at the property of an atom bonding to another atom. Okay, so let's have a look at electronegativity. You'll do this trend in detail next year, but pretty much if you want to know what is going to be more electronegative than something else, the electronegativity increases as we go across a row or across a period. So a row is a horizontal row, and that's called a period, and it also increases up a group. So the columns are groups, and so what would be the most electronegative element? Good one there, Max. Good try. And I can see why, because it's the highest one and it's the furthest to the right. The only thing is, remember, it's the bonding electrons, and because it's bonding electrons and helium does not bond, it's considered not to have an electronegativity because it's not measurable. Okay, no, you know, that's sorry, I was being mean. I was deliberately actually hoping that somebody would say helium, because that would make, you know, everybody realize group 17 is where it stops. So sorry for using you as my guinea pig. So fluorine is the most electronegative. Okay, and then oxygen is also pretty electronegative. Chlorine is as well, but what also comes into play is the size of the atom, and as we go down there are more electrons, so the atom gets bigger. So oxygen can do things that chlorine can't, because it's a smaller atom and the electrons are close. Those bonding electrons will be closer to the nucleus, so it has a greater effect than chlorine has. So these are considered the most electronegative: nitrogen, oxygen, fluorine. I know some German YouTube videos include chlorine, but we don't in New Zealand. Okay, right, we looked at this last week and you are welcome to play with it. As I say, Google FET and molarity or polarity, something, a molecule polarity. It is Java based, so your computer may not like it, your security settings may not like it, and if you've got an Apple or a Mac, they won't accept Java. So you could perhaps try it in a library if they allow it. Okay, so here's an example of oxygen, and we want to work out if it's polar or not. So the first thing you draw is the Lewis structure. And remember, how do we start with the Lewis structure? What is the first step in the Lewis structure? What do we count first before we even start the Lewis structure? So Michael is typing the valence electrons. Where do we find out the valence electrons? How do I know what the valence electrons are from oxygen? So Michael's typing again. but anybody else is also welcome to answer. You use the periodic table because remember the groups will tell you what it is. Group 1, 1 valence electron. Group 2, 2. Group 13 is 3. Group 14, 4. Group 15, 5. Group 16, 6. Group 17, 7. And then group 18, 8. Okay, you then work out the electron geometry. Now, if you've got two atoms in a molecule, it can only be linear. Okay, and so the molecular shape will be linear. Is there a difference in electronegativity? No, because they're the same element. So spell that out. I find often a lot of students don't spell out the obvious because it is so obvious. So but say it's the same atom, so there is no difference in electronegativity. Or they are both oxygen atoms, so there is no difference in electronegativity. Okay, so the bond is pure covalent, or there's equal sharing. So they have the same electronegativity, so there's no bond dipoles. So here I'm trying to represent the oxygen atom, and you can see it's all uniformly green, and it means there's an even distribution of electrons around it. It's a symmetrical molecule. Remember when I spoke about symmetry last time, I said draw a line along any bond and bisecting any bond. So here I've only got bonds, you know, one double bond. So if I draw a line along the OO axis, can you see this top half is the same as the bottom half? And if I bisect that bond and I draw a vertical line through it, then can you see the right-hand side is identical to the left-hand side? So do you agree that that shape is symmetrical and that molecule is symmetrical? Yep. Okay. And so is there a molecular dipole? So does the molecule have a separation of charge? No. Correct. Okay. So the molecule is nonpolar. Right. Let's look at another one. Okay. So we've got HCN, and we start off with the Lewis structure. And it'll come up with a triple bond to make sure that every atom has an octet, so 2, 4, 6, 8, 2, 4, 6, 8, and of course hydrogen only has 2. Okay, now think of the central atom is carbon. How many regions of negative charge does carbon have? 2. Well done. Okay, it was a bit of a trick question. I just wanted to see if you saw this triple bond as one region of negative charge. So we've got one region on this side, one region on that side. So what would my electron geometry be? Would it be linear? Would it be trigonal planar? Would it be trigonal pyramidal? Would it be tetrahedral? Or would it be bent? So I've got two areas of negative charge, both wanting to repel each other as much as possible. It'll be linear. Okay, and the molecular shape will be linear. Okay, so I see quite a few are typing and trying to get ahead. Thanks. Now, now we've got two different types of bonds here. We've got a CH bond and we've got a CN bond. Is the CH bond polar? In other words, is the electronegativity the same between carbon and hydrogen? Okay, basically at level 2, you can assume that every atom has a different electronegativity. So if I've got two different types, well, sorry, not every atom, every element. So if I've got carbon and hydrogen, they are two different elements. So I am going to have a difference in electronegativity in this CH bond, and so there'll be a bond dipole. Same thing for the CN bond. Do you notice I'm spelling it out? So make sure you spell out all the detail. So the CH bond is polar and the CN bond is polar because there is a difference in electronegativities, as all three have got different electronegativities. Okay, so you spell it out. NCH all have different electronegativities, so the CN bond and the CH bond are polar. and therefore there'll be a bond dipole in each bond, and this is what it turns out to be like. Hydrogen always gets the short end of the stick. It's the most polar. You can see it's blue. The nitrogen is the most electronegative, so it's the most red because it's got the most electrons. And can you see this yellow line sort of sticking out? That is showing the molecular dipole. We always show a dipole going from positive to negative. So, is this molecule symmetrical? No. Correct. You can, if we draw a line along this axis, okay, this top half does equal the bottom half, so there is a plane of symmetry. But if I bisect through here, through the carbon, okay, or any one of these sort of bonds, but through the central atom, you can see the right-hand side is not the same as the left-hand side. So the molecule is not symmetrical, so those bond type dipoles cancel. Now it's very common for students to say, the bonds cancel, and so blah blah blah. I'm afraid if the bonds cancel each other, everything's going to fall apart. Because bonds are the sharing of electrons, or if it's an ionic bond, that's what's holding the molecule together. So if the bonds aren't there anymore, it's not going to be a molecule. So remember to say the bond dipoles cancel. That separation of charge cancels out. It's like a tug-of-war team where the tension in the rope is the bond dipole, but the rope is the bond. Okay, so if you've got an equal sharing, equal tug-of-war team, and one's pulling one way and the other one's pulling the other way, if they're equal strength, that tension is there, but it's centered on that central point. So we consider them to cancel each other because there's no overall or resultant effect. Okay, and the rope, of course, is always there. That's the bond. If I've got a tug-of-war team that's uneven, so my ropes are still there, okay, but now what's happened is the stronger team has moved. Normally they always tie a ribbon or something in the middle of the rope. It has moved that ribbon more to the side. So you've got that molecular dipole. I don't know if that image makes it easier to remember. We're talking about the tension in the rope, and it's a stronger tension going one side. Okay, so here we've got now formaldehyde or methanol. So you count the number of valence electrons, you've got to distribute them around, and you're going to find you need to make a double bond to give everything an octet. For the oxygen an octet, the carbon an octet, and of course hydrogens have doubled. What is its electron geometry? So look at the central atom and how many regions of negative charge is around that central atom? 3. Correct. Now for excellence and so on, don't just say there are 3 areas of negative charge around the central atom. Show that you haven't learnt it, that you understand what's happening. So say there are 3 regions of negative charge around the central carbon atom. Can you see just that extra word shows you've understood this molecule, that the carbon is in the center and the other atoms are around it. Okay? I know for some of you it looks just so obvious that carbon must be the central atom, but spell it out. And they always assume a teacher or examiner is really dumb and you've got to spell out every little thing. Okay, it's a trigonal planar, and the molecular shape will also be trigonal planar because there are no lone pairs around the central atom. Okay, different atoms or different elements. So is there going to be a difference in electronegativity? Yes. And so will there be bond dipoles? Yes. So spell it all out. Oh, I can't spell have. That's HCNO all have different electronegativities. So spell out that those bonds are polar, and so spell out that there are bond dipoles. So there's a bond dipole going from the hydrogen to the carbon, and another bond dipole going from the hydrogen to the carbon. and a third bond dipole going from the carbon to the oxygen. And if I add all those vectors up, all those bond dipoles up, I'm going to have a much more negative charge over here where the oxygen is. So you now look at the symmetry of the molecule. So if I cut it down this CO bond, I think you all can see the left-hand side looks like the right-hand side. But remember, you've also got to cut it along the CH bond. So does this side look the same as this bottom side? No. And so it's not symmetrical. Similarly, if I cut it along this CH bond, this side does not look the same as that. So it's not symmetrical. So it's an asymmetrical molecule. By the way, asymmetrical, I still remember my university lecturer saying, only S's spell asymmetrical with two S's. So it always helped me remember it's got one S and two M's if you want the spelling. Quite a few students tend to write non-symmetrical. I think that's sort of come from America, but sort of the New Zealand is very based more on British English, even though we spell sulfur with an F. So we say asymmetrical. They won't mark you wrong if you say non-symmetrical, but it's not the right terminology we use. Okay, and so the bond dipoles don't cancel, and so there is a molecular dipole, that yellow thing sticking up there, so the molecule is polar. Okay, let's do, I think this is the last one, PCl3, phosphorus, group 15, so 5 valence electrons, chlorine, group 17, so 7 valence electrons, 7 3s are 21 plus 5 from the P is 26 electrons, and hopefully you can count 26 electrons there. Every line, of course, represents 2 electrons. Now, what is the electron geometry for PCl3? Would anybody like to have a go? Is it linear? Is it trigonal planar? Is it trigonal pyramidal? Or is it tetrahedral? Or is it bent? Emma, you are correct. There are 4 regions of negative charge. So yes, the electron geometry is tetrahedral. And Abigail, you're answering my next question now. So the electron geometry is tetrahedral. So the bond angles will all be 109 degrees. Okay. But the molecular shape is what Abigail said, the trigonal pyramidal. Because now, once we've done the electron geometry, we say, okay, right, there are 3 bonding pairs of electrons and 1 non-bonding electron pair, so it's going to be trigonal pyramidal. Okay. Now, are these going to be polar bonds or non-polar bonds? The PCl bond. So you can say P or NP, polar, correct, because they are different elements, so it'll be a difference in electronegativity. And Cl, I mean, you could just simply say that it's a difference in electronegativity between P and Cl, or you could say Cl is more electronegative than P. You're not expected to know the exact electronegativities. And because we've got a difference in electronegativity, we have bond dipoles, because they're polar bonds. And so if we look at the molecule, okay, we've got an area that's quite positive, that's the phosphorus, because that's the least electronegative, and then we've got the, I've gone blank, the chlorines, that are more electronegative. So we're going to have a bond dipole along this PCl bond, along that PCl bond, and along that PCl bond. And sorry, it's going from the positive to the negative. So it's going from the phosphorus out. So overall, these are pulled downwards. So the negative charge is more on the bottom, and it's positive on the top. So again, looking at symmetry, yes, I can cut it sort of through there, and this side looks the same as that side. But remember, you also need to cut it along each bond. So along this PCl bond, you can see this side does not look the same as that side. So is it a symmetrical molecule or asymmetrical? So Nicholas is typing. Asymmetrical. And then you put that final little thing, the bond dipoles don't cancel, so there is a molecular dipole, so the molecule is polar. Okay, or you could say, so the PCl3 is polar. Try and avoid pronouns or things wherever you think there could be ambiguity, always spell it out. So I should really say, so PCl3 is polar, just to be very clear about what I mean. Okay, do you think you can work out the polarity of molecules and write it out? Because this is what gives you your achieved merit or excellence. If you don't say very much here, you only get achieved. If you say a fair amount, you get merit, but if you say all of this, you get excellence. Do you think you can follow this pattern? So, wow, great. Okay, just practice the pattern. Do lots of writing, because the exam is going to be writing. Practice by writing. Okay, I know I hate teaching for exams, but because these lessons are so condensed, I really feel it's the best way to do it. So here's examples that I've actually taken from students' work. See how you can improve these statements. Methane is nonpolar as the bonds cancel. What is incorrect there, apart from too little explanation? So Emma's typing, the bond dipoles cancel. Correct. So if the person had said the bond dipoles cancel, they may have gotten achieved for this. At the moment, the stands are not achieved. They may have gotten achieved if they said the bond dipoles cancel. To get more than that, you've got to talk about electronegativity, you've got to talk about symmetry, and so on. So here CHCl3 is nonpolar as the shape is symmetrical. What is wrong with this? Because this is at the moment is incorrect. It's a not achieved. Now I know it's quite hard in that you don't have your Lewis structure. You can frantically draw your Lewis structure of this if you like. To work out those different steps. It is asymmetrical. Okay, if it was CCl4, it would be symmetrical, but CHCl3 is not symmetrical. Yep. So great, Nicholas. And again, if they said it was polar as the shape is asymmetrical, you may get an achieved, but certainly not a merit or excellence because there's not enough explanation. CO2 is actually I should have given the answers here. So bonds can't cancel, electronegativity not discussed, nor shape, nor symmetry. So you certainly won't get merit or excellence, and they were incorrect, so it's not achieved. And so I'm saying, although the shape, a tetrahedral shape, could be symmetrical, the molecule is asymmetrical because it's got two different types of elements bonded to it. Okay. So CO2 is nonpolar as there are no dipoles. What is not very clear in that answer? Okay, CO2 is linear, but can you see what did the student mean by no dipoles? Were they referring to the molecular dipole, or were they referring to the bond dipoles? Because there are bond dipoles, and the bond dipoles cancel, but there's no molecular dipole. So again, Abigail, you said there are no dipoles, but again, it's clear that there are bond dipoles, which cancel each other out because they're equal and opposite, but there is no molecular dipole. Yeah. So it's not clear what the student is referring to, and then of course they haven't discussed electronegativity and symmetry. Okay, so at the moment those are all not achieved. Okay, PCl3 is polar as the dipoles don't cancel. Now this has got a number of errors. No, sorry. This one has got no errors as such in it. But what? How could the person have improved this? I mean, all these others who were real sort of errors. Well, I suppose this one isn't too bad, and so it has the same problem here. But this one may be borderline achieved, but it depends on anything else. Okay, So I see Michael and Abigail are typing. I'm just going to put this in there because I do want to go on, but again, it's this bond dipoles and molecular dipole problem. Be very clear and specific, okay? And again, they've got to discuss electronegativity and symmetry. So, okay, it is asymmetrical and the bond dipoles don't cancel. Yep. And then you would talk about the fact that there's a molecular dipole. You would have to discuss why there are bond dipoles in the first place. So you have to talk about electronegativity. So you have to do all those different steps. If you just write something like this down, ask yourself why. So if you say bond dipoles don't cancel, say, well, why is there a bond dipole? Why, well, we've answered why they don't cancel because he said it's asymmetrical. But say, answer the question, why is it asymmetrical? So can you try and just use those why questions in your head when you're trying to answer so that you can get more detail down? Okay, so what I want to go on to now is the type of attractive forces between particles and therefore the solids that are formed because of those different types of attractive forces. So we see different substances having different properties. So that's what we call the macro level of what we see, what we feel, and so on. So what you need to do now is explain it on the submicroscopic level. In chemistry, it's always M, and M, okay? Macroscopic, microscopic, actually submicroscopic, but anyway, and model. So model are your formulae and equations, submicroscopic are all your particles, so you can't see it, but you're trying to explain the behavior. So if you like, the facts are what you see, the macro, sulfur is yellow, okay, hydrogen burns, and so on. That's a fact. What we do on the microscopic level are explanations, that's theory. So it's an explanation which works very well, and so we keep on using that theory. But if the facts change, if we start measuring something different, then we would have to change our theory. So that's sort of the way the science goes. So you need to, if you get given a fact, you need to be able to explain that fact based on what science knows so far. So there are the 4 different types of solids that we've classified. Ionic solid. So an ionic solid is something with cations and anions. And I've just done a 2-dimensional layer here where every cation would be surrounded by an anion and every anion would be surrounded by cations because opposites attract. And we'll go into that more detail. Metallic solids, those are all your metals, your gold, your copper, your silver, your potassium, all the metals, aluminium. Okay. Your covalent network solids. These are not that common actually, and they tend to be based around the ones with the highest valency. So carbon and silicon. A common question I get asked is, Miss, how do you know if something is, and I'll just go to the next one, how do you know the difference between a covalent and a molecular solid? When is it covalent, when is it molecular? If it has carbon or silicon in, then it's possible to form the covalent network solid. The other elements, non-metal elements, tend to form molecular solids because only carbon and silicon can form lots of bonds. There may be other network solids from other elements, but they certainly aren't common. So diamond, for example, is one. Graphite is another. Silicon dioxide, which makes up sand, is another network solid. So it's basically non-metal atoms covalently bonded together in a great big lattice structure. And molecular solids are basically molecules, okay? So often the name is quite clear. Ionic solids consists of cations and anions, in other words, ions. and the bonding is ionic bonding. So what's holding those particles together? The cations and the anions are ionic bonds. So in this column here, I'm going to write the particles in the substance, and this will be the attraction that's holding the particles together. So if I've got ionic solids have cations and anions, what sort of bonding does metallic solids have? Start with an easy one. Anybody want to have a go? Metallic solids, what sort of bonding? Would metallic solids have ionic bonds in them? Would it have covalent bonds between the particles, or would it have metallic bonds between the particles? So Abigail is typing, because you've only got those three types of bonding. To metallic, correct. So the particles are metal ions. So I'm trying to show, and there's big debate all the time in chemistry whether you talk about metal ions or metal atoms, because the metal cations, like copper 2+, has different properties to the copper in a metal. So it's not quite a Cu2+ ion, it is sort of in between. So they will, depending on the examiner, but they're normally quite lenient on this. Metal ions or metal atoms, both are accepted, the last I heard. They don't like it if you just simply say ions and delocalize electrons. You're going to state that it's a metal ion. So these are or metal core atoms I've also seen as well. So what happens is your metal atoms are squashed so tightly together that their valence shells all overlap. And because their valence shells now all overlap, the electrons can move merrily between them, and they're not stuck to any particular atom. So like this electron can move freely along, it doesn't get stuck to that atom, and some other ones will move around and take its place. So it's what we call delocalized electrons. They are not localized. They are not stuck in a local. They're not local, they're global. Okay, and it's metallic bonds. So Abigail is typing there, so I'll answer your question soon. The covalent network solid, what do you think those particles? Abigail, yes, if you said the metal nuclei, I think that would be acceptable. If you just simply said nuclei, that would be wrong, because now you're just looking at a nucleus, where it's actually the nucleus and the electron energy levels, but not the valence one. So you've got the nucleus and energy levels, and then you've got the valence electrons that are overlapping and moving around. Okay. But I think if you said metallic nuclei, that would be fine. Okay, what sort of particles would we find in a covalent network solid? Is it an ion? Is it an atom? Is it a molecule? What sort of particle? Anybody want to have a go? The Michael, atoms, correct. And more specifically, what sort of atom? Metal atoms, non-metal atoms, or any atoms? Non-metal, correct. So specify non-metal atoms. Don't just say atoms. Again, I'm not sure if they mark you down if you say atoms, but certainly if you're trying to go for excellence, and I always encourage all my students to do that, the more specific detail you add, the better. It just shows you've understood the work. And the bonding is, I think, quite obvious, covalent bonds. So the atoms, the non-metal atoms, are being held together by covalent bonds. So all these lines here are represented by covalent bonds. In graphite, you've got solid lines, which are the covalent bonds, and then you've got these dotted lines. And so you can get a mixture of attractions in covalent network solids, but the dominant one that makes it a covalent network is the fact that it's got a covalent bond. Okay, so your polymers, your 2D and 3D polymers fit in over here as well. Not so much your linear molecules. So polythene doesn't really fit in here, but certainly the cross-linked ones that in your tires and so on would be. Then your molecular solids, this I don't know if you can see is water, and it's actually ice. So you've got the water molecules here. What particles are in my molecular solid? Okay, they are molecules. So Abigail, it's non-metal atoms for covalent, but it's molecules. I know molecules are made up of non-metal atoms, so in a way you are correct. But we're going to be looking at the particles and the attraction between the particles. And what determines the property is going to be the attraction between the molecules, not the covalent bonds. So it's the molecules are the particles, and it's the forces between the molecules that give it its properties. Okay, so all these bonds will give the properties of the solid. So intermolecular, it's like the internet. Okay, you sitting all in different homes all over the place, and the internet is connecting us, but we're all separated, so it's between, the internet is sort of the connection between all of us. So it's not within a molecule, it's between molecules. Okay, so what I want to do today in the remaining 15 minutes is look at the first two, and then the next lesson I want to look at the covalent and the molecular solids, because this intermolecular forces has got quite a bit of detail. So, ionic solids, remember we said what are the particles? Cations and anions. So this is just very level one going over it. You've got metals, because they've got few valence electrons. You don't need lots of energy to remove those valence electrons, so they're going to lose electrons to form cations, rather than gain electrons to get a full energy level. So it's basically all the metals. They would rather lose the electrons to form a cation than try and add lots of electrons on. So sodium is an example. So sodium, its atomic number of 11, so it's got 11 protons, and therefore in a neutral atom 11 electrons. That one gets lost, giving me a full energy level of 2.2,8. Okay, and we can represent it like that. Sodium has lost an electron to form the sodium cation. So that's sort of basic background, and that's just say that's the one that's lost, and that's where that electron is. Okay. Any questions on cations, how cations are formed? Nope. Okay. I know there was a question that was sent in saying, well, why, these ones down here, gold, for instance, has got a valency of 1, why, and so, actually doesn't have a valency of 1, it has a valency of 3, and it tends to be quite unreactive. The ones down here tend to have quantum mechanics being much more important for quantum theory, whereas the other ones follow the sort of more basic chemistry rules. So the rules start changing as we get into these elements, and particularly as we get to the bottom, and then of course right at the bottom they tend to be all radioactive anyway. Okay, right, and that's just the thing to show full energy level there. Right, anions, what sort of metals, okay, I haven't quite given the answer there, what sort of elements gain electrons? Metals or non-metals? Non-metals. Okay, so because they're on this side, they only need to gain a few more electrons, and so they'll get a full energy level after just gaining a few, rather than losing all the electrons to empty out an energy level. Okay, so oxygen is an example. If I have 8 protons in oxygen, I've got 8 electrons in a neutral oxygen atom, and to get a full energy level I need to add 2 more electrons to get to 8, and so that 6 becomes 8, and those are the 2 extra electrons gained to make it go to 8. Okay, any questions about, going to form anions? So if I have something like magnesium chloride, what sort of substance is that? Ionic, metallic, covalent network, or molecular? Ionic, because magnesium is a metal and chloride is a non-metal, so a metal with a non-metal, ionic. Okay, so use your periodic table. And of course your cations and your anions attract, so that's just a little cartoon. So you've got all the non-metals over here with the anions and all the cations over here. Okay, and basically what I'm trying to show here then is if I've got a cation, it's going to get surrounded by anions. Front, back, top, bottom. Think of it three-dimensional. And every non-metal is going to, every anion is going to get surrounded by cations. And so what I'm just trying to show here, the cations are being surrounded by the anions, and the anions are being surrounded by the cations. And I hope you're getting the picture. So that's just what's happening on a two-dimensional layer. But remember, in front of this anion, there's going to be a cation. Behind this anion, there's going to be a cation. And the same thing for this. In front of this cation, there's going to be an anion, and so on. So do you get this idea that it's a lattice in 3 dimensions? And you must stress that in your answer, that it's 3 dimensions. Because if it was 2 dimensions, take this anion. How many ionic bonds do I need to break to separate out this anion? So assume there was another row in front. How many would I have to? 4. This one for one above, this one to this cation, this one to that cation, this one to that cation. But it's in 3 dimensions. So if you think of another layer on top and another layer behind, how many do I need to now break? 6. Okay. And of course, every ionic substance is different, so they pack a little bit differently. But you can see, I think, that in 3D you've got more bonds to break than in 2D. So stress that it's 3D because there are more bonds, so you need more bonds to break if you're trying to break up the substance. So what I've got here, and I'm just going to, just because it's pretty, I'm going to start from round about 30. You can't hear the lovely music, I'm afraid, but it's, I thought, very pretty. This is how the ionic bond, how they, they add on in 3 dimensions. So get this idea of 3 dimensions. Okay, you can look it up yourself if you like with this, if you Google that on YouTube. Yes, that's copper sulfate. Okay, and what I've got here is there's actually a place in Mexico. There's a cave that goes quite deep down, and they've got these most enormous crystals on them. So you have this, crystals being formed all over the place. That's the size of the man in there. And, just look at the size of those crystals. I would love to go there, but apparently you can last only between 5 and 10 minutes in there, and then you'll die from overheating. It's apparently incredibly humid and incredibly hot, and that's what maintains the crystals. Okay, so let's look at ionic bonds and ionic solids to see how we can explain the macro properties of the solids based on the theory of ionic bonds. So remember, ionic bonds between a metal and a non-metal, transferring electrons to get full valence energy levels between cations and anions, and they're very strong because all bonds are electrostatic. It's just with a cation and an anion, it's a very strong electrostatic because it's from a full positive charge to a full negative charge being attracted. So it's got quite high Coulomb forces. Coulomb for the physics people. If you don't do physics, don't worry about that term. So how can we explain the properties? Now if you think of what are the properties of an ionic solid? So you saw a few crystals there. Do you think we can shape them very easily. We can mold them, we can hammer them, and so on. No. Would they conduct electricity? No, not as a solid, and we'll explain all this why. And in solution, correct, Abigail. Would they, if I took a hammer to one, what would happen? It's brittle. It'll just break apart. Okay, you can hammer your salt. If you've got, these big rock salts in your kitchen, you take a hammer to it, you'll just powder it up. Okay, so let's try and explain these properties. So, as a solid, why doesn't it conduct electricity? And it doesn't conduct electricity because the particles, the ions, they're held very tightly in a 3D lattice. Spell out that 3D, okay? Don't just say they're held very tightly together. Because if you're saying it's in 3D lattice, it's being held in all parts around it. So it's not going to get out very easily, okay? And because, and what I didn't say here is, remember, electricity is the movement of charge, and ions are charged, and so these charged particles can't move. Okay, so there's no free charges like ions or electrons that can move. Good, Abigail. Right, and as I say, spell it out. In solution, it will, and we'll look at that just now. It's in our last point. Why are they brittle? If we take a hammer to them, why can't we mold it? Why does it just shatter? And again, explain if the lattice gets disturbed by taking a hammer to it or something, you shift the position of the ions, so you're suddenly going to get your cations too close together or your anions too close together, and instead of attracting now, you're going to have the opposite force, and they're going to repel, so of course it's all going to fall apart. So, I mean, I've just given very summarized here. You could explain in a bit more detail. High melting points, generally very high, okay, normally from 1,000 degrees up. Some are lower, but it tends to be high. And again, explain it's a strong electrostatic force, so you're going to need lots of energy to break it. And when you melt something, you're separating the particles. So in this case, you're separating the ions. So if you're separating the ions, you have to break all these bonds, ionic bonds. So mention the 3D lattice again. So because you can also explain in 3D lattice there are more bonds because it's being held in the front and the back and the sides, left, right, top, bottom, front, back. Okay. So you've got to break many of these bonds to melt a solid. And then the last one is the solubility. Now, not all ionic salts are soluble, of course. In fact, the more highly charged they are, or the smaller the cation or anion, the less likely it's going to dissolve. But generally, you could say that the attraction between, remember water is polar, so the attraction between the dipole, the molecular dipole of the water and the opposite ion. So if I'm talking about a cation, you're going to get the hydrogen side of the water molecule. That will be a form of strong enough attraction and lots of attractions that energy released, because when we make bonds, we're releasing energy. So that energy released is enough to supply the energy for breaking the ionic bonds, so between, say, the sodium and the chloride, all those bonds, and between the water molecules. Because remember, the water molecules are also attracted to each other. So we want to break those solvent-solvent bonds, and we want to break the solute-solute bonds. And when we've now got our ions in solution, we've got our cations surrounded by water molecules and our anions surrounded by water molecules, and they're now free to move. So it will conduct as a solution. So all those things you sort of need to explain. Now I see we've hit 12 o'clock, and it was partly because I started a bit late, but I want to stop there, and I think the next lesson I'll just focus on the other three solids, and then we'll have one more lesson in the series on thermochemistry, and then we can move on to the next standard. So, any questions on polarity and on ionic solids? Okay, Abigail's typing there. You're welcome to send any questions through at any time, and I can include them in my lesson. So, you know, that's totally feasible. Okay. Yes, this one you will, because I've shared my screen. The lesson I did yesterday, I uploaded the PowerPoint, and I'm struggling to make the PowerPoint show in the recording. So once I get that sorted, and hopefully I will get it sorted, I'll upload that one as well. But that's why I haven't uploaded the other one yet on the internet, on YouTube, because it's, you see me and you see your chat, but you don't see what I'm trying to share. So I'll download this overnight and then put it up onto YouTube tomorrow. Okay, well, have a lovely lunch. And what I'll do for next week, because Monday's a public holiday, on Tuesday I'm going to do the other 3 solids, and I'm going to do, because Monday's a holiday, I'll do the 91161 on the Thursday. It's just going to be for next week that it's on the Thursday. I just don't want people to get too behind. Okay, I will be sending the links out as I'd record them and put them on YouTube. I put them up on Ottel, the news channel, and then I send out 1 email a week with the links. Otherwise, if you just search for my name, so just do Delene Holm on YouTube, then you'll find all my videos. Now, a lot of my videos are level 3, because I've always done the level 3 online lessons, but I'll be starting a playlist for level 2 once this one's up, because then I'll have 2 in the playlist. So you just look for the level 2 playlist, and then you can see that. Okay, right, you have a good lunch. Bye everyone.